Here's a sheet of ordinary graph paper, and on the graph paper I have drawn a cliff, and at the top of the cliff I have a little cross representing a cannonball, and we're going to fire the cannonball off the cliff horizontally at a velocity of 30 meters per second. Now this is physics world, so we're going to simplify, we're going to ignore air resistance, and we're going to analyze the path of the cannonball and its motion as it falls. The interesting thing about projectile motion is that you can analyze the vertical motion and the horizontal motion completely separately. This device will drop one ball straight down and fire the other horizontally. Hopefully we should see that they both hit the desk at the same time. 3, 2, 1. The horizontal motion didn't affect the vertical drop at all. And that's why over here I've produced these two tables that record on the top the vertical motion and the bottom the horizontal motion. I want to see where the cannonball is and how fast it's going in the horizontal direction after 0, 1, 2, 3 or 4 seconds here, and after 0, 1, 2, 3, 4 seconds here, what its vertical velocity and displacement are. Let's do the horizontal motion first, because that's the easy one. How fast is the cannonball going horizontally? Well, it starts with a velocity of 30 meters per second, so I can write 30 in there. And then what goes in the other boxes? Well, there's no air resistance force acting, so there's no reason for that velocity to change. I just write 30, 30, 30, 30, 30. And now, what about its displacement in the horizontal direction, the horizontal component of displacement? Well, at the start, it's got 0 horizontal displacement, but then we go 30 after 1 second, 30 meters, after 2 seconds, 60 meters, after 3 seconds, 90 meters, and after 4 seconds, 120 meters. Not too scary, hopefully. Okay, what about the vertical motion? Well, we're going to assume that the gravitational field strength, which is equal to the acceleration due to gravity, is 10 meters per second squared on Earth. So we're going to start with a vertical velocity component of 0. Hang on, why 0? Well, it's because at the beginning it's not moving vertically, it's got a horizontal velocity but no vertical velocity, so it's going to start at 0. But every second it's going to get 10 meters per second faster. So 0, 10, 20, 30, 40. Now, depending on how algebraic you want to get, you can work out the the displacement component in a number of different ways. One way you could do it is to say, after 0 seconds, the displacement is of course 0. It's just at its starting position. During the first second, it starts at 0, and after 1 second, it's moving at 10 meters per second. The most common mistake people make here is to say, oh, so it must have fallen 10 meters. No, why not? It's because it wasn't falling at 10 meters per second for that whole second. It started from rest, and only by the end of the first second was it falling at 10 meters per second. The average velocity during that second was only 5 meters per second. So in the first second, it only falls 5 meters. What about during the second second? Well, it started at 10 meters per second, and by the end of the second second, it was traveling at 20 meters per second. So what was the average velocity during that second? Well, 15. It will fall another 15 meters during that second. 15 plus 5 is 20, so 20 goes here. And likewise, during the third second, it must fall 25 meters with an average velocity of 25 meters per second in the vertical direction. 45 is the next number here, therefore. And in the fourth second, 35 meters. So we should get 80 there. And that's a nice starter exercise for this part of the for this exercise. Okay, so now we've got velocities and displacements both in the horizontal direction and in the vertical direction. You could also get these numbers if you wanted by using the formula S equals a half a t squared, depending on whether you've covered that already. It's the area under the velocity time graph. So the next bit, having got this information, having got these numbers, I would now get the pupils to plot well, is it a graph exactly? Let's say a sort of diagram. I say take these rows here, the displacement rows. Using this, we can see that after 1 second, the ball will have gone 30 meters horizontally and 5 meters vertically. Let's plot a cross where the ball will be after 1 second. Well, the scale is 1 big square to 10 meters, so let's count 10, 20, 30 meters horizontally and half a square, 5 meters downwards. There's my first cross. Boing. Now, what about after 2 seconds? Well, it's gone 60 meters horizontally and 20 meters vertically. Another 3 squares, 1, 2, 3, 20 meters from the top, 10, 20. It's going to be right there. 3 seconds, 90 meters, 45, 70, 80, 90, 30, 40, 45. And you'll notice that I've cunningly scaled the paper so that everything should fit. And then after 4 seconds, 80 downwards and 120. So that's 120. That's 50, 60, 70, 80. Oh, look, it just fits. That's lucky, isn't it? There we go. So now let's draw a curve through these points. Our best curve, trend line, whatever, yeah, curve of best fit. What is it? What is this line? Oh. It is important that it's a nice smooth curve, so I've done it wrong. My pupils do it a lot better than this. There we are. Oh, nice. 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 It's a curve. It's clearly a curve. What sort of a curve is it? Ooh. Ooh. It's a parabola. Nice. And so what does this curve represent? Well, it represents the path of the cannonball. This is where it is after 0 seconds. This is where it is after 1 second. I'll even draw it. T equals 1 second. This is where it is after 2 seconds. This is where it is after 3 seconds. This is where it is after 4 seconds. So the curve represents the path of the cannonball. Right, this next bit is really important. If you don't do this, your pupils will get the exercise all wrong. I know this because I did this for years and years and I didn't do this and my pupils all got the exercise wrong and I had to correct them and it was all kind of disturbing to the pace of the lesson. So get them to turn the piece of paper over. Yes, turn it over so that you can't see the curve anymore. Don't let them do the next bit without turning the paper over. If they won't turn the paper over, make them. Right, this next bit is great because it uses a ruler and tracing paper. This is one of the few physics uses for tracing paper that I've found. There is another one, but this is my favourite. Right, take the tracing paper, and we're going to draw on the tracing paper some vector diagrams. And what are the vector diagrams going to represent? They're going to represent the velocity of the cannonball after 1 second, 2 seconds, 3 seconds, and 4 seconds. How do we draw the vector diagram? We draw them tip to tail. So after 1 second, the horizontal velocity was 30 meters per second, wasn't it? Yes. Let's label the vector. Nice. Now, the vertical was 10 meters per second, not 5. This is the velocity, yeah? 10 meters per second. 10 meters per second, there we are. And so our resultant will be like this. We could measure it as about kind of 33, 34 meters per second, but the important thing is to draw the vector diagram there. That's the resultant velocity. And we can draw all the other vector diagrams. Velocity after 2 seconds. Of course, this one is, they don't actually all have to be to the same scale if you don't want them to be, but maybe it's better if they are. Don't join them up though, it's better if they're separate. For some reason, lots of people want to join them up. I'm not quite sure why, but it's better if they don't. Okay, this is the best bit. Now, and only now, you turn the paper over. There we are. And now what do? Now we float the tracing paper over the curve at the right point. Oh. You can make a copy of this on an overhead projector and do it in front of the class. It works quite well. Oh, look at that. Oh, look at that. Oh, look at that. What is the relationship between the resultant velocity vector and the curve? Well, look, the resultant velocity is a tangent to the curve at every point. You've got to float it over at the right point, but when you do that, you see that the velocity vector arrow is in the same direction as the curve at that point. And this is a productive point to ask your class, why? Why is that? Well, think about it. What does the vector diagram show us? It shows us the velocity at that moment, what we might call the instantaneous velocity. And what does the curve show us? Well, that shows us the path of the ball. At that particular moment, after exactly 1 second, the ball is traveling along the curve in this direction. If we could switch gravity off at that moment so that the ball experienced no forces after this moment, it would come off and carry on traveling in the same direction. Newton's first law. That's the direction it is traveling in at that moment. So no wonder the arrow is tangent to it. It is the instantaneous velocity at that point, and it tells you what direction the ball is traveling in at that moment. After 2 seconds, it's traveling in that direction. After 3 seconds, it's traveling at that direction. And after 4 seconds, it's traveling in this direction. And this little exercise just gets your pupils to think about what instantaneous velocity might mean and why the diagrams match up so nicely. And it is a productive way, I have found, of opening up these questions to discussion, as well as getting some practice in drawing some vector diagrams and thinking about velocity, displacement, and all that good stuff. Who will I use this exercise with? Well, it's pretty good for a Year 12 class who are starting in on the mechanics aspect of the A-level. However, I've also often used this with Year 10 classes. If you're going to do vector diagrams, this is a good example of tip-to-tail vector addition if you introduce it in a reasonably non-frightening way.